So, good day. Uh, ang i-discuss natin ngayon, today we're gonna be discussing about the fundamentals of solar collection and thermal conversion. So, we already had the calculations during our face-to-face class. So, today we are gonna be discussing more on the concepts, terminologies that are essential in this lesson, which is again fundamentals of solar collection and thermal conversion. So, first we have to discuss the physics of the sun and its energy transport. So, we all know that the nature of energy generation in the sun is a subject of ongoing scientific inquiry, and the composition of the sun is 80% is hydrogen and 19% is helium. And how do we have the energy, or how do we basically have the energy emitted by the sun? So here it says that the sun's energy is generated through a hydrogen to helium thermonuclear fusion reaction. So in this process, hydrogen nuclei collide under extreme conditions to form helium. Then it releases vast amounts of energy in the form of light and heat. And the formation of solar phenomena such as prominences and sunspots, which play significant roles in the sun's activity, also continues to be a subject of active research. So yun nga, we know that we knew that to have, or for us to have that solar energy, the sun is having a nuclear fusion from its hydrogen and helium chemical makeup. So once they fuse, then that's the time it will release vast amounts of uh, energy, again in the form of light and heat. And despite this uncertainty surrounding the exact mechanisms of energy generations, the specifics of energy distribution are of greater concern to those who study the sun's effect on Earth. So, yun nga, syempre, uh, it's not really about energy generation of the sun, which is the concern of many, but it is how this energy gets distributed on each part of the earth. Because again, our target is to harness this maximum energy depending on our location. So uh, the main study that we are doing is to have that energy distribution, so that we know where to install what at what location does the solar energy hit, and that we can capture the most. So yon, and the sun is a vast sphere with a diameter of approximately 1.39 million kilometers, composed of multiple gas layers that become progressively hotter towards its center. And the outermost layer, from which energy radiates into the solar system, has a temperature equivalent to 5,760 Kelvin, or around 10,400 degrees Rankine. Imagine, this is a lot. This is really a lot of energy that we can harness. So if we really utilize this, then it's really enough for us to have a large amount of uh, energy that we can utilize in the world. And since this is the case, this is the reason why we are studying where could we get this maximum temperature, or at what maximum temperature does so sorry at what temperature can we harvest uh, on a specific location. Kasi if you could still remember, 'di ba, our formula for energy being radiated on a specific area is the Stefans Boltzmann constant, or the Stefan Boltzmann constant. That is E, then sorry, that's the sigma, then the emissivity factor, then the area, then the difference, that's the temperature difference of the temperatures. So, 'di ba, this is our formula. So the reason why we need to know at what temperature can we really harvest that energy. So the total rate of energy emission from the sun is around 3.8 times 10 to the 23rd kilowatts, which comes from the conversion of about 4.3 times 10 to the 9 grams of matter per second into energy. And despite this, imagine this big amount, uh, only a small fraction at 1.7 times 10 to the 14 kilowatt reaches Earth. This is most likely half, more than a little from the half of the value, which is located approximately 150 kilometers away from the sun. So that's still far. It's that's really far. So our mission or our target is to have this uh, harnessed as much as we can. So, yon solar energy is the most abundant and permanent energy source on Earth, with the amount intercepted by the planet being 5,000 times, with the amount intercepted by the planet being 5,000 times greater than the combined sum of all energy inputs, such as nuclear, geothermal, gravitational, lunar energy. So uh, imagine how much of a solar energy uh, we can have if we really can harness this. This is 5,000 times greater than all of the systems that we have here. And of the solar energy that reaches Earth from that 1.7 times 10 to the 4 kilowatts, 30% is reflected back into space, 47% is converted into low temperature heat and re-radiated into space, and 23% drives the evaporation and precipitation cycles that sustain the biosphere. And less than 0.5% of the solar energy contributes to the kinetic energy of wind and waves and in photosynthetic processes that store energy in plants. So imagine that is the contribution, the energy distribution that reaches the earth. And more of this, kung mapapansin nyo, if you can see, is re-radiated into space. This re-radiated into space and reflected back most of those energy. So it really has a lesser amount that reaches to uh, us, to our solar energy system. So more of the energy is just being reflected back, and the amount of energy that falls on Earth's surface is still immense, though only a fraction is usable due to physical and socio-economic constraints. Yeah, that is right. Since uh, approximately one third of the total extraterrestrial solar radiation reaches the Earth's surface, with 30%, so with 70% of it falling on the oceans. However, the remaining energy strikes land about 1.5 times 10 to the 17 kilowatt hour is staggering. This energy is already enough. This and really roughly 6,000 times that, excuse me, times that the total energy consumption of the US in 2009. Despite its abundance, only a small portion of this energy can be harnessed for practical use due to limitations related to technology, infrastructure, and societal factors. So, here it was discussed that even though there are still a lot of energy, or there are a lot of energy reflected back to our space, still the energy that reaches or that falls on Earth's surface is still immense, or it is still high. It means it is high that it could provide roughly around 6,000 times of the total energy consumption of US. So imagine 6,000 times, and US is a first world country, so they consume a lot of energy a year. So imagine having 6,000 times of that the sun can provide to us. If we have specific, or if we have proper technologies, then that would be a lot, that would suffice our needs. But then again kasi it's because uh sorry this energy still is a lot, especially that, imagine if this 70% does not fall to oceans but rather falls to a specific land surface where solar panels are installed. So that means if we can harvest that energy, then that means it really is a lot. It can it can maybe it might be, sorry, it might be able to supply or to supply our energy needs for lifetime. That in that numbers, that is really a lot. So yeah, that's it. And again, uh if we're talking about energy and we are talking about sun, then we are also talking about thermal radiation, because again, uh the energy from the sun is transmitted to the earth via radiation, because again of that fusion. So how can we measure that thermal radiation? So radiation uh, includes or travels at the speed of light, constant denoted by a c sub zero in a vacuum, which is approximately 300,000 kilometers per second, or uh, 3 times, excuse me, times 10 to the 8 meter per second, or 300 times 10 to the 6 meters per second. So this relationship between the speed of light, wavelength, and frequency is fundamental, because again, we have to measure radiation. And the speed of light in a medium equals the speed of light in a vacuum divided by the spring refractive index of the medium, which is this. C equals uh, this, or the C sub zero over N, wherein this representation provides a wavelength, then V represents the frequency, excuse me, and C is the speed of light. So this is basically a, a measurement of our thermal radiation. But again, if we are talking about energy being released by the sun, it still boils down to our heat transfer through radiation, which is uh, this. It's not discussed here, but in the book, it is discussed. It's here. Let me show you our reference book. It's here. So this should I we are still we are still planning, because yesterday Sir Barreto and I had discussed about this. He mentioned to me that we need to integrate this calculations, this in this part. Yeah, this part. We need to integrate this. We need to integrate this part in our discussion, since again we are talking about fundamentals. Since we are talking about solar radiation and solar collection, we need to know we need to know the energy of a photon, wherein this is equal to h times the frequency v sub p, wherein h is a Planck's constant. So this is one of how we measure the intensity. But as you can see, since the energy, uh, we still have a lot to consider on this, especially the wavelengths of what is being emitted, or what is being transmitted to the Earth's surface. So yun, we need to consider a lot for this. Yeah, we need to consider a lot for this, and we are having uh, Sir Barreto proposed to have a separate discussion regarding this. I opened it to him that the ideology regarding this is more already on the heat transfer part of your subject, but he is trying to he wants you guys to still know this, because again we are talking about solar energy, so we need to have the fundamentals like this black body radiation So we are gonna be utilizing this. So if he still insists on having this one discussed, so we will be having a separate discussion for this if we still have time. So we'll be having a separate discussion regarding this, the energy density. So yeah, this one will be again we'll be having a discussion, a separate discussion regarding this when there's still time because he proposed to have this one discussed as well. So we'll be using this and this. This is just the total energy emitted by a black body. So syempre, ito naman, this is just the same formula of our heat transfer through radiation, which is the Stefan Boltzmann constant and the temperature to the fourth power. The emissivity factor on a black body is just equal to one. So the reason why when we evaluate the integral of this, it's just gonna be this formula, and this is already in terms of watts per square meter since we are talking about energy density. So yan. So we'll not be dealing right now for this as well as this radiation factor function tables. So we're going to be discussing this and also this. If we still have time, we're going to be dealing more about this and the shape factor. So this intensity of radiation and shape factor, we're going to be discussing this again if we still have time. But until only here, that we are going to be discussing. Yeah. So up only until that because after this is uh the geometric relationship na. So that we have already discussed during our face-to-face class. So yon. And thermal radiation is a form of electromagnetic energy emitted by all bodies due to their temperature. So when a body is heated, its atom, molecules, or electrons become excited, meaning they are raised to higher energy states. Those excited particles eventually return to lower energy state, and in doing so, they release energy in the form of electromagnetic radiation. Then, these specific changes states result from alterations in the electronic, rotational, and vibration states of atom and molecules. And like what we have discussed on lesson 1, di ba? Yung energy changes vary depending on the mechanism and the radiation emitted by a body is spread across a range of wavelengths. It depends whether it is this. Let's just go back fast here. Ah, ito, in lesson 1 natin. Yan, ito. Itong mga spectrum na to, it depends on this kinds of radiation on the UV radiation, the visible light, and infrared radiation because this affects the quality of solar energy that we can harvest from the sun. We are gonna be talking about that later on as well. So, yon. Balik tayo. So, Yun. So, again, those wavelength range from zero point 0.1 to 3 micrometers, where most of its energy is concentrated. And most likely, the emitted uh, spectrum or the emitted wavelength that reaches the Earth's surface is the visible light. So we have to harness that, and as well as we need to either minimize or maximize the infrared and the UV. So it really depends on the application. So yun. Then ito, Sun-Earth geometric relationship. So we have discussed this that the amount of energy that we can harness depends on the position of Earth with respect to the Sun. Since the Earth's annual orbit around the Sun is elliptical, meaning that the distance between the Earth and the Sun changes throughout the year. This is already visible, or this is already cleared out during our face-to-face class. You can see that once the Earth revolves around the Sun, it has different declinations. So it really has different measurements or different distances from the Sun. And This variation influences the amount of solar radiation intercepted by the Earth. So during the winter solstice, approximately December 21, the Earth is at its closest point to the Sun, known as perihelion, with a minimum distance of 1.471 times 10 to the 11 meters. So I just want to clarify this. Remember this. Kindly remember this. Winter solstice occurs at December 21. That is right. And but it's not on the winter solstice. Remember this, it's not on the winter solstice that the sun or that the earth is at closest point to the sun, meaning it's not December 21 that is closest point to the sun. The event where the earth is at its closest point to the sun is during perihelion. And perihelion is uh typically occurring, remember this, perihelion, perihelion is occurring during January 3rd or 4th. So remember this again, winter solstice is uh, occurs approximately on December 21 or 22. But this does not uh, this does not mean that that is the time that it is at the closest point to the sun, that the earth is at the closest point to the sun. It's not the case. It's just that uh, winter solstice starts at December 21, but at the closest point to the sun is during perihelion, which occurs on January 3rd and 4th. So Yon. And usually perihelion happens at about 2 weeks after the winter solstice. So, uh, if you could imagine, why does if we are talking about the distance from the Earth, di ba? If we are talking about the distance from the Earth, why is perihelion not causing summer, di ba? Why is it like that? Why is perihelion not causing summer? Eh, di ba? When we say perihelion, it's closest to the sun. So it's basically closest to the sun. So be uh it should be causing summer, but hindi po. It's not causing summer because our seasons tandaan, our seasons are uh our seasons are based on the tilt axis of based on the tilt of Earth axis. So this is the main reason. And even though, tandaan, even though during perihelion, the Earth is the closest to the sun, it experiences winter because it receives less direct sunlight due to the actual tilt. Kasi 'di ba, if we draw uh if we draw in solar declination angle when we during the discussion. So for example, this, 'di ba? Then nandito here is the sun. So as you can see, uh it's tilted, though it's near, or the position of the earth is at the nearest to the sun, but as you can see, the earth is tilted backwards. The earth is tilted backwards, so it has a lesser time, or it has a lesser daylight time, because again this is tilted backwards, and that is that is the basis of our seasons based on the tilt of the earth. And again, since during this time the earth is tilted backwards, then there is a short amount, or there is a short amount of daylight during perihelion. So that is the reason why that is called the winter, or that is occurring after the winter solstice, because again during perihelion there is a lesser daylight time because of the tilt of the earth. So yeah, that is the reason why. And the other one, the Earth the Earth is at its farthest point from the Sun, called aphelion, with a maximum distance of 1.521 times 10 to the 11th meter. And this one naman, when we talk about summer solstice, that starts to occur at approximately June 21, 'di ba? That approximately occurs during June 21. However, however, guys, this is not really the case on uh this is not really the case during Aphelion, because Aphelion is not on June 21. Tandaan, Aphelion is not on June 21. Uh, when does Aphelion occurs? Aphelion occurs during, remember this, Aphelion, Aphelion occurs during early July. That's basically 2 weeks as well. 2 weeks as well from 2 weeks from the summer solstice. So, yon. Again, summer solstice occurs at June 21, but that doesn't mean that it is at the closest point to the sun, or that it is at the farthest point from the sun. It is the aphelion, it, wherein the event, wherein the sun or the earth is at its farthest point from the sun. So, and that aphelion again occurs during early July. So, again, why does this not causing winter? Malayo nga siya, or why does this uh, aphelion not causing winter if it's at the farthest point? Because then again, if we try to look at the position of the earth, for example, this is the sun and this is the earth, it's leaning towards the sun, it's leaning towards the sun. So since this is leaning towards the sun, this is tilted towards the sun, our earth, during this time, during June 21 and during early days of July. It means there is more daylight during these days, more daylight in aphelion, more daylight, and this is aphelion, more daylight. It means there is a longer time, a longer daytime. So that's it. Whereas in perihelion, the one that we discussed earlier, there is uh, more night time. So that's it. The reason why during perihelion, this causes, or there is an occurrence of winter, because there is more nighttime, because the earth is tilted away from the sun, though. And on aphelion, though it is at the farthest point, it is leaning, or it is leaning towards the sun, which causes more time, or more daytime. So that's basically the difference between the two. And sir, why do we not harvest more energy, or we not why can we not harvest energy more on winter solstice uh than summer solstice? Basically, again, because of the tilt of the sun. Though theoretically, the sun, or during during perihelion, the sun can receive more amount of energy from excuse me, more energy during perihelion. That is uh how do you say this? Sorry, I'm getting lost. So in perihelion on January 3rd and 4th, based on studies, it really can harvest 7% more solar energy than in aphelion, which is the summer solstice. But that 7% more is quite smaller if we think about the tilt angle, because the actual tilt of the earth is the actual tilt of the earth dictates more of the energy uh being directed towards the Earth because again, although perihelion uh, has during perihelion the Earth emits, or the Earth can receive 7% more solar energy. It's just that that value is uh, quite smaller if we consider the tilt angle, because again there is more exposure of the sun during 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 aphelion, or during summer solstice. The reason why it's not really considerable, or it's not being considered to have more energy in perihelion than aphelion. So yun, that's basically it, because again the very reason is that the energy is more likely to be harvested, or more likely to be at the maximum, depending on the actual tilt of the Earth, depending on the solar declination angle as well. So the higher the declination angle, the the more the Earth is tilted towards the sun, so it will have a longer daytime, so we can harvest more energy from the sun. But in perihelion, since that is leaning away from the sun, so there is a shorter daylight hour, so there is a lesser time for sun's exposure. The reason why it's more, or it's less solar energy that we can harvest during that time. So that is basically the difference between the two. I hope that is clear. So yon. Yun nga, sabi dito, due to the varying distance, the intensity of solar radiation intercepted by the Earth fluctuates throughout the year. When the Earth is closer to the sun, the solar radiation received is at its maximum, which occurs around December 21. But then again, uh, when the Earth is farthest from the sun, or farther from the sun, the radiation received is at its minimum, which occurs at June, sorry, which occurs around June 21. But then again, this is quite different when we are talking about the harnessed energy, because again during December 21, or during summer solstice, there is a shorter daytime. So if we collect that maximum amount, that will still less than uh, the amount that we can harness during June 21, because during this day there is a longer daytime. So that is basically the difference. But then again, if we are talking about the solar radiation received, it is at maximum during December 21. But uh, do, but if we are talking about the solar radiation be accumulated in a day, we can harvest more on June 21, because we have a longer daylight because of the actual tilt. And the variation in solar radiation is a direct consequence of the inverse square law, where the intensity of radiation decreases with the square of the distance from the source. Despite these changes, other factors such as the tilt or of the Earth's axis and its rotation play a more significant role in determining seasonal temperature variations and climatic patterns rather than changing Earth-Sun distance itself. Seasonal temperature variations and climatic patterns. So, naulit lang, sorry. So, yon. Again nga, the tilt angle is uh, the one that uh, dictates the seasons of the Earth. That is at 23.45. So, we already know this. And the distance between the Earth, that is aphelion and perihelion, the maximum and the minimum. Then, yan, we have already discussed this, the solar declination, during our face-to-face classes, as well as our azimuth and zenith angle, our R angle, we have already discussed this. Then the solar time, we already discussed this. So you may have a read as well on this, but we're going to be skipping this since we have already calculated this during our face-to-face classes. So Yon. Now, we talk about solar thermal collectors naman. Ang solar, the difference between solar panels and solar thermal collectors and solar panels. In solar panels or in our photovoltaic systems, we are more into uh, getting the energy from light. However, from solar thermal collectors, we are harnessing energy from the heat as the reason why it's called thermal collectors. So we are harnessing solar energy from its heat. So yun nga, the conversion of sun's radiant energy is into heat is a practice with historical roots that has evolved into a sophisticated solar conversion technology in modern times. The fundamental principle underlying solar thermal collection is straightforward. When solar radiation strikes a surface, a portion of the energy is absorbed, causing an increase in the surface temperature. So, yun. And the effectiveness of a surface as a solar collector, however, depends on more than just its ability to absorb solar radiation. A key determinant of its efficiency is how well it minimizes thermal and radiation losses to the surrounding environment. And a wide variety of solar thermal collectors have been developed to meet diverse needs. This range from unglazed flat plate collectors, which operate at 5 degrees to 10 degrees above the surrounding ambient temperature, to excuse me, to advanced central receiver systems. The latter utilize concentrating collectors to achieve operating temperatures exceeding 1000 degrees Celsius. So these types of collectors, we are going to be discussing this on lesson 3. The flat plate collectors and uh, the concentrating collectors. So we are going to be discussing that when we do lesson 3. But for now, we are going to be discussing about the radiative properties na lang or radiative properties of our solar thermal collectors. So, what is this? So, uh, when radiation strikes a body, hold on, wait for a minute. Yeah, and when radiation strikes a body, the energy is distributed among three distinct processes: reflection, absorption, and transmission. And part of our radiation, uh, we discussed earlier, when it hits the surface, it gets only reflected. And there is also a part where it is absorbed by the material. And if the material is transparent, then it will transmit through it. So this three, reflection, absorption, and transmission, is gonna be equal, or the summation of this will be equal to 1, which is equal to the total radiated energy. So the fraction of the incident of radiation reflected by the surface is called reflectance. Ibig sabihin, uh, it is reflected by our solar thermal collectors. The energy is being reflected off the surface. Whereas if we talk about absorptance, it represents the fraction of radiation absorbed by the material, contributing to its internal energy and raising its temperature. And whereas transmittance naman corresponds to the fraction of the radiation that passes through the material without being absorbed or reflected. So, ito, yun nga, gaya na sabi natin kanina, this is bounded by the first law of thermodynamics because it's just equal to the energy in equals energy out, that that it cannot be uh, destroyed, cannot be created as well. So, yeah. And this should be equal to 1 nga, guys, like what I have mentioned earlier. So let's dig deeper about this three. What is the importance of these characteristics of materials? So when we talk about reflectance, let's write it. When we talk about reflectance, then uh, it is necessary, like what we have mentioned, this is the energy of the reflected by the surface. So if the material is or has high reflectance, so it means high reflectance high reflectance means there will be a lot of wasted solar energy. Whereas kapag or if we have low reflectance, then more energy will be absorbed or will be utilized, will be absorbed. So that that's it. So what again is the importance of this? And in our solar panels and in if we talk about solar panels, okay, if you talk about PV systems, let's write this is the main difference. When we talk about PV systems or solar panels, photovoltaic systems, if we talk about photovoltaic systems, then it should have anti-reflective coatings. It means the material that we have to use on our PV systems should have anti-reflective coating so that all the energy will be absorbed. However, if we are gonna be talking about concentrating solar powers, like what we discussed on lesson 1, or the CSPs, since we are using mirrors, 'di ba? During CSPs or concentrating powers natin, or during solar thermal collectors, we are using mirrors. And since mirrors have high reflectance, so during or with the design of concentrating solar powers, we need to have a high reflectance because that mirrors or the energy will be reflected towards our concentrator. Towards energy will be reflected towards our concentrator. Kasi nga, if you could still remember, and I hope you should, I hope you are, or I hope you still remember that. Kasi 'di ba, I drew that one. For example, we have this parabolic trough. So there is this mirror is here. So when the energy or the solar radiation strikes here, it needs to reflect the energy to our tubes, to our receivers, so that when it gets reflected, the tubes will be the one being heated. So we need to concentrate the energy. The reason why on concentrating powers and solar thermal collectors, we need to have high reflectance materials to reflect the energy towards our concentrator. Then if we talk about absorptance naman, if we talk about absorptance, let's put it here. Here. Absorptance. So, like what we have mentioned earlier, uh, absorptance. Higher absorptance means, high absorptance means we can, uh, more energy can be converted since we absorbed it. Whereas if it's low, then it's the opposite. Less energy converted. And less energy converted. And one of the properties of our materials should be dark colored materials. We know that dark colored materials absorb more sunlight. So that means we need to have those dark color to absorb more energy from the sun. So, how can we apply this on our systems? So, in PV systems, that is that is the reason why we use silicon, because semiconductor materials absorb uh, energy more, or absorb more sunlight compared to other materials, because semiconductor materials have high absorptance. So the reason why we are using silicon on our solar panels or in our PV systems, whereas in our solar thermal collectors, we are using a selective coatings like this. We are going to be discussing that later on. This selective surface, because we are coating our collectors with selective coatings like black chrome or titanium oxide, so that it can absorb heat. It can absorb more heat because, again, dark colored materials absorb heat. That is why during selective surfaces or selective coatings, we use solar, or we use uh, black chrome or titanium oxide to absorb more heat. Whereas when we talk about transmittance naman, it corresponds again to the fraction of radiation that passes through the material without being absorbed or reflected. Why is it important? Uh, in when we talk about PV systems, or in our solar panels, or uh, photovoltaic systems, we have to minimize our transmittance uh, to make sure that all the energy is just being absorbed, because if this just passes through our surface, then it will not be converted into electricity, simple as that. So we need to minimize transmittance for our PV systems. However, uh, when do we need to have a high transmittance? We need to consider high transmittance only if we are uh, if we are having, or if we are planting trees, like for example. So if you are going to be covering that, or if you are going to be doing greenhouses, for solar greenhouses, you need to use materials with high transmittance, so the sunlight could pass through. So that's when you use a high transmittance. But if we are gonna be using, or if we are gonna be relating it to solar energy utilization, we need to have, or to minimize transmittance, because what we need is for the energy to be absorbed so that it can be converted to solar, or into usable energy. So that's it. And another important uh, radiative property nga is called emittance, which is the ratio of the radiative emissive power of a real surface to that of an ideal black surface. And yun nga, emittance natin is uh, commonly equal just to 1 as well, uh, for an ideal black body surface. So, yeah, selective surfaces naman are specially engineered to maximize energy efficiency by combining two key surface characteristics. So, like what I have mentioned earlier, uh, we use selective coatings because we need to have a darker surface so we can absorb more energy. We are using selective surfaces to absorb more energy so that we can convert more energy. So that is a selective surfaces. So yun nga, these are designed to exhibit a high absorptance for solar radiation, which predominantly consists of short wavelengths, while simultaneously maintaining a low emittance at the operating temperature of the surface. So the principle behind this selective behavior lies in the distribution of energy across different wavelengths nga. So 98% of the energy is concentrated in wavelengths below 3 micrometers. Oh, excuse me. In contrast, the radiation emitted by black or gray surfaces predominantly occurs at wavelengths longer than 3 uh, micrometer, accounting for 99% of their emitted energy. So here, on our selective surfaces, basically, if we need to have selective surfaces uh, that is at high absorptance in the visible spectrum, because that is where the most solar energy is, and lower emittance uh, in the infrared spectrums for us to reduce heat loss. Again, that is the function of selective surfaces. To have high absorptance in the visible spectrum, kasi as we have checked back earlier, that is where most solar energy is during at visible spectrum. Whereas we need to also have low emittance in the infrared spectrum to reduce heat loss. And application of this is yun nga, in our solar thermal collectors, uh, we use black chrome or black nickel and titanium oxide coatings. And for our photovoltaic system or our solar panels, we use uh, semiconductor materials, which are silicon. So yun. How about reflecting surfaces? So in reflecting surfaces, it is rely on optical components to direct and focus sunlight onto a smaller targeted area, maximizing energy collection. So this is just uh, commonly used in collectors. Nga, like what I have mentioned earlier, we are using reflecting surfaces to redirect the sun's energy. For example, when it hits the mirror, then the heat will be reflected to our concentrator, which is a tube wherein there is the fluid. There is the fluid that is being heated. So doon, hinihit yung fluid. So uh, all of the energy will be reflected to that. So it will be receiving more uh, heat. So that is just a reflecting surfaces. So most likely this is made by mirrors. So also from highly polished metals or consists of metal coatings applicable to suitable substrates. So when an opaque substrate is used, the reflective coatings must be applied to the front surface. So yan. Again, the basically the concept regarding reflecting surfaces lang is that it should be, or our solar thermal collectors should have this, so the energy will be reflected towards our central receiver where our fluid is being heated. So that is reflecting surfaces. Whereas transparent surfaces, uh, this is again, transparent materials are for transmission purposes, to pass through a certain material with minimal absorption or reflection. Then again, like what I have mentioned earlier, if there is a higher transmission or higher transmittance, then more sun will be able to pass through it. More sunlight can penetrate. So where do we use again this? We use this on solar greenhouses where when we plant trees. So we use transparent materials for the sunlight to pass through for our plants in our solar greenhouses to undergo photosynthesis. Uh, in terms of PV panels, we also use a transparent glass covers so that when it penetrates towards that transparent glass, then the heat will be trapped inside. Then all of those the light will be trapped inside, and all of those trapped will then be absorbed by our silicon or our semiconductor materials. So that is the purpose of uh, transparent materials. Again, we use transparent materials in our photovoltaic systems, on our PV systems, based on we are using that to trap all the all the sunlight that passes through it, and all of those sunlight will be then absorbed by our semiconductor materials. Whereas in that same goes with our solar thermal collectors or our concentrating solar powers. We use a transparent covers to let sunlight in while we trap the heat there. So basically we are trapping the heat so that no heat will be reflected back, or no heat will be uh will be reflected back, or will be radiated back into space, so that we can utilize more of it. And I think that's the end of lesson 2. So lesson 3 will be discussing this uh next meeting. So yun, I hope you understand the lesson, and yun, thank you, and that's it for lesson 2.